On April 10, 2019, the European Commission and the Event Horizon Telescope team revealed something we had never seen before. A real image from deep space at 53 million light-years away.
And this is what everyone was looking at, the center of the distant galaxy M87, the very first image of a supermassive black hole. This gave us direct evidence of a black hole, because before this, black holes were only an idea. Scientists could measure its mass with much better accuracy, and black holes turned out to be round, exactly as Einstein's theory of relativity predicted.
Every galaxy we've had the capacity to check has revealed a black hole to us. Thus, we will extrapolate and assert that a black hole is a natural phenomenon in the center of all galaxies of the universe.
But Professor Nicolas Poplawski takes that idea even further.
Every black hole creates a new growing universe inside the event horizon.
That what we perceive as the Big Bang wasn't the beginning from nothing, but the bounce from another collapsing universe.
That matter after the bounce has to expand somewhere, so it expands into a new space.
And at the furthest edge of what we call the universe could lie the other side of a black hole. And that's where today's journey began. So welcome to this full-length documentary. Black holes are among the most extraordinary phenomena in the universe. They represent regions where gravity becomes so extreme and space and time themselves begin to bend.
It forms boundaries where the known laws of physics begin to collapse. In Stephen Hawking's collected scientific papers from the book Hawking on the Big Bang and Black Holes, one of his most striking insights concerns the nature of phenomenon. He stated that the early universe cannot have been completely homogeneous and isotropic, because galaxies and stars would not have formed. Here, Hawking and his collaborator Jonathan Halliwell emphasized that tiny irregularities in the early universe were essential. Without them, the perfectly smooth cosmos would never have evolved into galaxies, stars, or any large-scale structure at all. These minute fluctuations also opened the path for black holes. Unlike galaxies that radiate light and matter outward, black holes trap everything that comes too close. Once something crosses the event horizon, there is no return.
And so, inside this boundary, the roles of space and time effectively reverse, and the common rules of escape no longer apply.
Understanding this brings us to the core idea of how they interact with the fabric of space-time, which is based on Einstein's special theory of relativity. This theory suggests that space and time are woven together into a four-dimensional space-time continuum, with 3 dimensions for space and 1 for time.
When we introduce mass into this fabric, something special happens due to the way energy interacts within it.
Einstein's theory tells us that space isn't flat, just as Minkowski's space suggests. Instead, it bends around objects. So in this view, gravity isn't just an invisible force acting over a distance, it's actually the result of the curvature of space-time, with this term being the curvature tensor, and this one is the energy density tensor. We can observe that the curvature of space-time increases with an increase in energy density. As gravity is an effect of the curvature, the more energy an object has packed into it, the stronger its gravitational pull becomes.
And this is the fundamental reason behind the theoretical concept of a black hole. This incredibly dense object forms when a massive body collapses to a specific size, something known as the Schwarzschild radius. General relativity not only forecasts the existence of black holes, but also outlines their structure within the Schwarzschild metric. This metric is a specific solution to Einstein's field equation. If you're overwhelmed by this equation, don't worry, I've got a simple explanation for you. You see, this equation predicts that a black hole has 2 parts.
The event horizon, which behaves as a boundary between a black hole and the rest of the universe at this radius. The singularity, where the entire mass of the black hole is predicted to exist.
The black hole is a region of space and time where the strength of gravity is so high that light has no path to get out of the object. All paths through space-time curve back in on itself. That edge, beyond which there's no return, we call the event horizon. You can think of a black hole as completely consuming the volume of space-time in its vicinity.
But how can a black hole continue spinning indefinitely while remaining stable over time? So, to answer this, he defined measurable physical quantities that described a black hole.
And those are mass, the surface area of its event horizon, angular momentum, and the electric charge.
From these, they derived a set of equations linking these quantities together, producing what are now known as the four laws of black hole mechanics. If you ask me, these laws in some way extend the four laws of thermodynamics.
The 0th law. The surface gravity of a stationary black hole is constant across its event horizon. This means that the gravitational pull at the edge of the black hole is uniform everywhere when the black hole is in a steady state. No side exerts a stronger force than another. The 1st law. Any small change in a stationary black hole's mass is exactly balanced by changes in its horizon area, angular momentum, and electric charge.
From here, we know that this relationship acts as a kind of ledger.
Even if an object falls into a black hole and is stretched into what physicists call spaghettification, the information it carries, like its mass, spin, and charge, is not destroyed. It becomes encoded in the so-called black hole's balance sheet. The 2nd law. The total area of a black hole's event horizon never decreases over time. When two black holes with areas A1 and A2 are merging, the resulting black hole has a new area, A3, that is greater than the sum of the two initial areas.
So, in other words, black hole horizons can grow, but they can never actually shrink.
The 3rd law. It is impossible by any physical process to reduce a black hole's surface gravity to 0 through a finite sequence of operations. No matter how you might try to manipulate it, like by spinning it faster or adding mass, you can never reach perfect stillness.
Achieving 0 surface gravity would require an infinite number of perfectly tuned interactions, and not to mention infinite time. So, if it were possible, it would expose a naked singularity, and at the same time violating the foundations of modern physics. If we look closely at 4 of these laws, they all converge on one key concept: the event horizon. Each law speaks about it, its gravity, area, or how it changes with mass, spin, and charge. And so the event horizon is the central stage where all of black hole mechanics take place.
If you went in across this region, 3 kilometers, you went inside it, you couldn't get out. So that's called the event horizon. So you wouldn't notice if you fell through the horizon of the black hole in the Milky Way galaxy.
Well, if a black hole's event horizon is basically the point of no return, our universe has something like that too. It's the limit of how far we can actually see. And I'm sure you know where I'm going with this. We call it the observable universe.
It's the cosmic bubble that contains everything whose light has had time to reach us since the Big Bang. And because the universe has been expanding all this time, that horizon stretches out to about 46 billion light years in every direction. Beyond this limit may lie regions of space that exist, but remained forever hidden from us, because their light has not yet had time to reach us since the Big Bang.
And so this leads to an intriguing perspective. The term event horizon describes the limit seen by an observer outside a black hole, while the observable universe represents the horizon for an observer within the cosmos itself.
In both cases, the boundary of what can be known depends on the position of the observer.
And this is perfectly consistent with the principle of relativity.
Time freezes and we cannot go beyond. If time on a spaceship crossing black hole freezes to 0 relative to our time, that means we will never see the spaceship crossing the event horizon. So basically, from our perspective on Earth, the spaceship will cross the event horizon after infinite future.
So how do black holes form? Well, it starts when a very massive star reaches the ends of its life. It explodes in a supernova, one of the most powerful events in the universe.
During a supernova, the star's outer layers are violently flung into space, while the core undergoes a gravitational collapse. But not all of these events have the same outcome. If the core's mass is several times that of our Sun, gravity's force overwhelms everything else, inducing the core to implode. This implosion is so severe that it shrinks the mass into an incredibly tiny volume. Think of it like squeezing a softball. When you squeeze it, the ball shrinks, but its mass, or the amount of material, remains the same. It just becomes denser. Now imagine you could squeeze that ball until it was as small as a grain of sand, yet it still weighed as much as before. This is similar to what happens when a massive star undergoes a supernova.
I don't think a black hole knows it's a black hole. It's just a lump of mass out there. If Earth today turned into a black hole, it'd be a mini black hole like the size of a plum.
Have you ever wondered why matter doesn't run out of space when it collapses during the formation of a black hole? Is there a point where it just can't be compressed anymore? Well, there is a limit to how much you can compress it, and this is connected to the different states of matter. For example, a rock maintains its rock shape due to the forces between its atoms and molecules, something known as electric forces. However, when under a lot of pressure, it can push atoms and molecules closer together. This squishes the space between them, a situation called electron degeneracy.
You're trying to cram electrons into the space of other electrons, and they don't allow that, all right, from quantum physics. They keep their own identity within the structure.
This kind of extremely dense matter can be found in white dwarfs, which are basically just the leftover core of a star like our Sun. Think of it like the massive space between an atom's nucleus and its electrons.
If an atom were the size of a football stadium, the nucleus would be a tiny poppy seed at its center, and the stadium walls would represent the electron orbits. This fact was uncovered by Ernest Rutherford. In his experiment, he shot particles at a thin layer of gold. What he found was that most of the particles zoomed straight through, as if there was nothing in their path.
The next morning, he is rumored to be afraid to step onto the floor, getting out of bed, that he might fall through it, because he alone knew how empty matter was.
The next stage of compression is cramming the electrons into the protons. The outcome of this high-pressure interaction, where a positive charged proton combines with a negative charged electron, is the creation of a neutral particle, something called a neutron. You might recall something as neutron stars. This name isn't random, since it's directly connected to the fact that these stars are densely packed with neutrons. What remains after a star has exhausted its life cycle is such a neutron star. These celestial bodies are incredibly dense. In fact, it's the densest known objects in the universe that aren't black holes.
Neutron star matter weighs about a mountain per teaspoonful. So much that if I had a piece of it here and let it go, and I could hardly prevent it from falling, it would effortlessly pass to the Earth like a knife through warm butter.
Neutron stars that rapidly rotate have magnetic fields that pulse. We call those pulsars. The person who discovered pulsars, Antony Hewish, won the Nobel Prize for it in the 1970s.
So, how dense is a neutron star? Imagine squeezing 300 billion elephants into something as small as a thimble. That's the kind of density we're talking about. And if you try to compress it even more, you're basically crossing into the black hole territory.
Black holes can vary in type and each possessing its own distinct size, formation process, and behavior. The most prevalent is the stellar black hole. Its mass spans from 3 to 10 times that of our Sun. These form when a massive star exhausts its nuclear fuel and falls inwards under its own gravity. The star then shrinks incredibly, packing a vast amount of mass into a minuscule volume. Typically, these black holes carry a mass several times that of the Sun, yet they're astoundingly small, just a few kilometers across.
This makes them insanely dense, which is enough to form an event horizon.
Then there are intermediate mass black holes. The exact mass of these black holes is uncertain, but it's thought to be in the thousands to tens of thousands times that of the Sun. And so, they're denser than stellar black holes.
How they form is still a puzzle, but there are two leading hypotheses.
One proposes that they result from several stellar mass black holes merging together. The second one suggests that they might originate from massive gas clouds in the early universe. collapsing inward to create a black hole instead of a star. Locating these intermediate mass black holes can be challenging, but there have been some indications of their existence observed indirectly, like observing the behavior of stars and gas near suspected locations of these black holes. At the top end of the scale, we have supermassive black holes. These are the big players, with masses millions to billions of times that of the Sun. They sit in the centers of most galaxies, including our Milky Way.
We're still not sure how this formed, but one hypothesis is that they grow from smaller black holes by continuously sucking in all matter from around them.
Last but not least, we've got charged black holes. These are interesting variations of black holes that have an electric charge. There are two main types: Reissner-Nordstrom and Kerr-Newman black holes. Reissner-Nordstrom black holes carry a charge, but they don't spin. General relativity describes them using what's called the Reissner-Nordstrom solution. Their charge influences their gravitational field, but in most ways, they're like uncharged black holes. They have an event horizon, but its size depends both on the black hole's mass and its charge. Kerr-Newman black holes, on the other hand, both carry a charge and spin. They're described by the Kerr-Newman solution in general relativity. The mix of charge and rotation creates unique phenomena around these black holes. One such effect is frame dragging, where the spinning black hole pulls and twists the surrounding space-time.
And beyond the event horizon, there is another boundary inside the black hole called the Cauchy horizon, an inner edge that marks the location of the singularity itself. So all of these types of black holes have one thing in common: the event horizon. As we all know, space and time no longer behave the way we expect there. There's no specific where or when. And this creates a strange sight for anyone watching from afar. As a person falls towards the event horizon, he appears to slow down from the outside, almost as if coming to a stop just before crossing it. He never seems to actually enter the black hole. He simply fades, growing dimmer until he vanishes from the view entirely. This strange phenomena is due to how black holes distort space and time.
It's still pointing to a deeper structure. There's something that it corresponds to in the fundamental nature of reality, that our perceptions map onto something. It's just not the experience of it that we're having.
And so this line of thinking leads to a compelling possibility that the reality we experience might not be the original structure. It might just be a projection.
So we might actually be in a simulation. Not like a digital one, but more like a physical simulation where the most fundamental level of reality is just 2D. That gets projected outward into a 3D universe, the universe that we somehow experience. And that's not even the weird part, because quantum mechanics already hints that space-time, energy, and mass are emergent things that arise from a more fundamental layer of information. But then black holes got pulled into this picture, and that's where it gets peculiar. Because when you combine these ideas, you end up with something called the holographic principle. You see, black holes are like glitches in reality. They seem to harbor multiple paradoxes on the inside that thankfully we can't observe. Black holes contain the most amount of stuff in the least amount of volume, and since everything is just information, then they should have a lot of them, right? But they don't.
This idea originally came from a puzzle in black hole thermodynamics proposed by Jacob Bekenstein and Stephen Hawking. They found that a black hole's entropy is proportional to the surface area of its event horizon, not its volume. The larger the surface area, the more entropy it contains. And as we all know, entropy is one of the metrics used to measure the information content of an object. And so, this led to a provocative conclusion. Everything that falls into a black hole might not be lost inside, but instead, its entire informational content is encoded on the surface, just like a 2D hologram that stores a 3D image.
It is possible mathematically to encode information about three-dimensional systems on two-dimensional surfaces, of how all the information on the one hand could be on the horizon of the black hole,
the idea that all of reality could be contained in 2 dimensions, and there's something about the interaction between different points that caused this holograph, so that it seems like there's a 3-dimensional world when in fact that it's a projection of this 2-dimensional surface.
In simple terms, everything that happens in a 3D space can be fully described by information stored on a 2D surface.
Which makes scientists wonder, why would a black hole be the only things that behave in this way? Why wouldn't everything else follow the same rules? I mean, look around you. Your phone, your bed, everything will be a hologram, an illusion, including yourself. There is a reason we don't see reality as it is. If we did, our minds wouldn't be able to handle it. Space, time, matter, energy, none of it may be truly fundamental. But one idea suggests that everything we see is like a projection from a 2-dimensional boundary of the universe, which holds all the information inside. And this boundary is called the cosmic horizon, and it is parallel to the event horizon. So does that mean we are inside a black hole? In 2014, astrophysicist Nicolas Poplawski published a paper titled "A Universe in a Black Hole with Spin and Torsion."
In it, he proposed a remarkable idea: that the interior of a black hole could be interpreted as a new, closed universe, born through a process known as a cosmic bounce. He introduced a modified version of the Friedmann equation, the one that governs the expansion of the universe. This equation serves to explain how this whole scenario could occur, as one of the criteria for its work.
But what does that really mean? Let's briefly dissect this puzzle.
When you hear the term black hole, you probably imagine a tiny dot that swallows everything around it. But mathematically, the situation inside a black hole is far stranger. Within the event horizon, the coordinate we normally call space begins to behave like time, and the coordinate we call time starts behaving like space. This means that once you cross the event horizon, you can no longer stay still. Everything is compelled to move towards smaller values of r. In the same way, we are all inevitably moving forward in time in this universe. And so, from that perspective, the interior of a black hole behaves much like an entire universe that evolves over its own time dimension.
But how does this swapping of space and time affect someone falling into the black hole?
Well, normally we can control how we move through space, but unfortunately not through time. I can decide to fly toward a black hole or away from it, but I can't stop myself from aging into the future. So once a person falls past the event horizon, he can't choose to move away from the singularity. But one thing for sure, he can still pick a path by adjusting his trajectory through time to get there.
This is the interior geometry that Poplawski is working with. And to describe what happened next, he doesn't use standard general relativity. He worked with a slightly modified framework called the Einstein-Cartan theory.
It preserves the idea of curvature, but adds an additional geometric property known as torsion, a kind of intrinsic twist in spacetime caused by the spin of matter particles. It is represented by this term in this modified Friedmann equation. For simplicity, this accounts for spin, torsion, repulsion, a kind of force that becomes significant at extremely high densities.
Torsion manifests itself like a gravitational repulsion, which means when the matter wants to create a singularity in a black hole, the matter reaches extremely high densities, much bigger than nuclear density, and then torsion, which is negligible.
Now, as matter inside a collapsing black hole is compressed to insane densities, Poplawski suggests that the effect of spin becomes dominant.
At some critical density, the spin-torsion repulsion becomes strong enough to halt the collapse, preventing the formation of a true singularity.
Mathematically, when the energy density epsilon equals the spin-torsion term, the contraction stops, at which A dot reaches 0. At that point, a bounce occurs instead of a singularity, where the scale factor A would otherwise shrink to nearly 0.
So what exactly is the deal with this? Well, in this description, instead of a usual singularity that we know, the interior of a black hole reaches the smallest possible size and then re-expands. You can think of this phenomenon as dropping a super bouncy ball. What matters is that the ball compresses at impact, and then it rebounds and flies back up.
Big bounce means very huge deceleration. Matter collapses very quickly and then suddenly it stops and bounces back. You go from contraction to expansion, so there's a huge acceleration. So gravitational field changes in time very, very quickly according to the Hawking radiation.
And this part really blew my mind.
As you've probably noticed, once the event horizon forms, nothing inside can communicate with the outside. Not even information, light, or quantum bits.
This means that whatever happens after the bounce, the so-called this new expansion or the created mini-universe, is completely invisible to the original universe.
But from the perspective of observers inside that newly formed cosmos, it would appear exactly like living in an expanding universe. They would see galaxies moving apart, the CMB cooling down, just like everything we observe in our own universe. According to Professor Poplawski, it's the truly mind-blowing fact that the interior of a black hole becomes a new closed universe.
And so what if our universe as we know it today is part of something like this?
That our reality now, or the scientific term of what we call the observable universe, is nothing but a closed universe inside the massive interior of a black hole, the one that exists beyond everything we know. So, to summarize, Nicolas Poplawski argues that the conventional idea of the Big Bang that we all know is actually a big bounce.
The formation of a new universe with a completely separate space-time structure. And all of that happens inside a black hole.
If singularity is avoided in a black hole and the matter bounces back and starts expanding, that matter after the bounce has to expand somewhere, so it expands into a new space.
Later in this video, we'll cross that boundary, beyond the edge of our universe, into the possible realm outside the black hole that could contain everything that we know. I mean, if our reality truly exists within one, it might just change how you understand existence itself. So stay tuned until the end.
In physics, a singularity refers to a point in space-time where certain quantities become infinite or undefined. We find such singularities in multiple theoretical contexts, such as at the inception of an expanding universe known as the Big Bang singularity, and also within black holes. When examining the Big Bang singularity, a significant challenge arises. The theory suggests that our universe emerged from an incredibly dense and hot state, approximately 13.8 billion years ago. But as we trace time back to this initial state, the equations of general relativity fail.
This suggests that our current understanding of physics can't fully describe the conditions at the Big Bang. So to actually figure that out, we need a theory that brings together general relativity and quantum mechanics.
When you think about black holes, as far as we can tell, they are a fundamental quality of the world, but you have to include quantum physics to truly understand them, and that's the cutting edge of what's happening right now.
According to Einstein's theory of general relativity, anything falling into a black hole, be it matter or energy, encounters this singularity. It experiences something we call infinite compression.
Now, this is the thing that really pushes the limits of what we currently know about physics. Like, the whole idea of infinite compression is genuinely hard to wrap your head around. But one way to imagine it might be through the lens of the movie Interstellar.
We see Cooper plunges into a supermassive black hole gargantua. The screen erupts in a vortex of light, which represents a visual of space-time being distorted. Once inside, he finds himself in a realm beyond normal comprehension. A space-time region that represents every moment in his daughter's bedroom all at once. A tesseract, if you will. This is a good depiction of how time and space might behave differently in the presence of a singularity.
Center black hole is a singularity. All the theories say the matter occupies zero volume, thereby having infinite density. That's a limit of Einstein's theory. That's where it breaks down. So in Einstein's equations, we're dividing by zero at the singularity. So we all know that as brilliant as Einstein was, and as successful as his general theory of relativity has been, it has limits. And one limit is the center of a black hole, and another limit is the very birth of the universe itself.
No matter what type of black hole we're talking about today, there's one concept that always comes up right alongside it, and that is dark matter.
It's a unique kind of matter that outweighs visible matter in the universe. We call it dark because it doesn't interact with light or any other forms of electromagnetic radiation. We know it's there because of how it impacts visible matter and the overall structure of the universe. Many suggest that dark matter had a key role in shaping galaxies and even forming black holes. One of these theories proposes that dark matter acts like a scaffold, with galaxies being built around it. Its gravitational force pulls regular matter like gas and dust together, creating large structures like galaxies. And as these galaxies evolve, the right conditions for black holes to form can emerge. In other words, dark matter, through its gravitational influence, is vital in determining how matter is distributed across the universe. It creates the perfect setting for black holes to form.
And another interesting idea is that dark matter might actually be made up of black holes that formed way back in the early universe.
If this is true, these black holes would have affected the dynamics of the early universe through their gravitational pull, potentially leading to the formation of more stars and galaxies.
There is a suggestion that the black holes themselves could be dark matter, meaning they are invisible and they could populate the universe almost arguably large enough to explain this missing mass, this missing matter.
Astronomers often watch the paths that stars take around black holes. They do this to spot the presence of dark matter. It has quite an impact on the way stars move within galaxies due to its gravitational pull. One thing that astronomers do is to study the gravitational effects from visible matter, like stars and gas clouds. If the star's motion doesn't line up with what we'd expect from the visible matter alone, it hints at the presence of something more. Perhaps that's where we'd find dark matter.
It's important to keep in mind that even though dark matter seems to be everywhere, it's not really thought to directly form black holes on its own.
Our current understanding is that black holes come about from the collapse of regular matter, like giant stars. But spinning and charged black holes might be related to dark matter in some way. The fact that they spin or carry an electric charge can prolong their existence. This could turn them into a possible source or storage for dark matter particles. It could possibly offer more insights into the character of dark matter and its role in shaping the universe.
We come across a compelling interplay between the forces of the cosmos and the counterintuitive rules of the quantum world. Because when you zoom into the incredibly small scale, black holes show another puzzle. And this time, Stephen Hawking came in with a theory that ties these two together. It's called Hawking radiation.
Imagine matter and antimatter particles suddenly appearing near the event horizon of a black hole. Usually these pairs would annihilate each other and disappear. But if one falls into the black hole, the other can escape. This escapee is what we call Hawking radiation. This is basically the gist of this theory. Although Hawking actually described this process more technically, he referred to the positive and negative frequencies of the quantum vacuum that get disrupted by the black hole. This disruption leads to the vacuum itself generating particles that we can detect.
Hawking radiation shows that black holes are not completely inescapable. They slowly lose mass over time because of this effect. This idea also helps answer a question that scientists have had for a long time.
It was initially believed that nothing could escape a black hole because nothing can move faster than light. However, Hawking radiation led most physicists to agree that the energy sucked into a black hole could eventually leak out.
I think most physicists believe that because you have this Hawking radiation, at least the energy that falls into a black hole can eventually leak away as that radiation. The really important thing about that is that not only can the energy get out, but the information can get out. This was the other perplexing thing about black holes.
Hawking radiation might also help preserve quantum information. This idea was a puzzling aspect of black holes. Quantum information shouldn't be destroyable, and many physicists now suggest that the details of what falls into the black hole could escape through Hawking radiation.
If you gather all the Hawking radiation from a black hole over trillions of years and place it together, you could theoretically reconstruct what initially fell into the black hole.
One description of how this happens is that the thing that falls into the black hole somehow gains negative mass or negative energy because the dimensions inside the black hole get all twisted around.
And in a popular interview, physicist Bryan breaks down what this really means.
If a super being in the far future could collect every bit of Hawking radiation that came off the black hole for trillions and trillions of years and stick it into a giant quantum computer, then they could reconstruct everything that fell in.
So in the following section, we're going to delve into the mind-bending topic of black holes Hawking radiation.
When black holes were first conceived mathematically, there's a question arose among physicists. Could these entities actually exist in the universe?
The math suggested that they were possible, but was there real-life evidence for it? It took 4 decades before we had tangible evidence.
In 1964, using advanced X-ray satellites, researchers detected an unusual source of X-rays in the constellation Cygnus. Despite the intense emissions, the object itself remained invisible. This puzzled the scientists, as a typical star emits both visible light and X-rays. They named this mysterious source Cygnus X1. Kip Thorne and Stephen Hawking even had this famous bet on what the object actually was.
There was a bet between Stephen Hawking and Kip Thorne. Whether or not we actually had the data justified for a black hole. So what was the first black hole?
Stellar mass black hole, so 10-ish suns with a star friend, and the black hole is slowly eating material from the star.
In 1970, astronomers Palmer D. and Louise Webster observed that Cygnus X1 was in a binary orbit with a nearby star. This relationship allowed them to measure its mass. Fast forward to 2021, it was confirmed that Cygnus X1 has a mass 21 times that of our Sun, making it the heaviest stellar mass black hole that was identified without gravitational waves.
The black hole also spins at a rate near the speed of light, faster than any other known black hole at the time.
Louise and I published a paper about the X-ray source Cygnus X1, which might be identified with this system that contained HDE 226868, and if so, and if all connected together in this way that we fantasized about, then the companion was a black hole.
Massive black holes are like internal entities. They never truly disappear. This is because anything they emit gets reflected back into them, and they continue to exist.
On the other hand, small black holes eventually vanish. They can't maintain their existence because they lose more energy than they take in. The thing is, whether it's a big or small black hole, all the information inside them remains intact. None of it just disappears into nothingness. So there's no paradox, and the fundamental idea that information must be conserved in the universe remains valid. Then, when we create a black hole in the context of conformal field theory, we can ensure that this evolution always keeps the information preserved. So information isn't lost, even in the complex world of black holes in anti-de Sitter space.
Now this might be the key to unlocking the mystery of the information paradox.
That's a good thing when things go from they often start out as very speculative, then they become something a little bit better than speculative, conjectural, and the end process is they just become a tool of physics. Things that everybody uses all the time because it has a predictive value, a mathematical value.
As we've seen before, black holes are defined by just 3 properties: mass, charge, and spin. This is due to the no-hair theorem, which tells us that the original details of the matter that fell into a black hole are lost, leaving behind only these 3 properties.
If you take 2 black holes, one from a massive star and another from a neutron star, they'd appear identical except for differences in their mass, charge, or spin. When we apply quantum mechanics and consider black holes as quantum objects, a whole new array of characteristics comes into play. Take entropy, for example. The entropy of an object is like the number of different ways its insides can be arranged.
To figure out entropy, you need to know how much an observer understands about the object.
For instance, take a randomly shuffled deck of cards. Describing the position of each card would need a lot of details. We can say that this order has high entropy compared to this one. But the no-hair theorem tells us that we can't get details about the matter inside a black hole. So black holes are thought to have maximum entropy.
As a black hole grows, its entropy increases, okay? So the amount of hidden information increases. And so there's this very tight relationship between actually the surface area of a black hole and the amount of stuff that it's eaten, which corresponds to the amount of information that that black hole is hiding.
So quantum field theory actually tells us that energy can exist in a vacuum, where pairs of particles and antiparticles randomly pops into existence and then disappear almost instantly. So even though all the mass of a black hole is packed into that singularity, these particle pairs can still show up and vanish within the black hole's vacuum.
The process doesn't usually have a noticeable impact if it occurs inside or outside a black hole, except when it happens near the event horizon. In that case, the intense gravity can pull one particle in while flinging its counterpart towards infinity. Since this pair springs from the black hole's energy, the escape of one particle will reduce the total energy of the black hole. This escapee contributes to what we call Hawking radiation. This is quite important for our discussion today. Hawking radiation implies that black holes can emit energy, shrink over time, and ultimately cease to exist. This means that it results in a fundamental loss of information. We lose the ability to pinpoint the precise quantum state of all the particles that once made up the black hole.
If you think of yourself as information, right? Let's say you burn a book and collect everything that comes out of the book, all the ashes and all the gas and everything. Then in principle, you can reconstruct the book. Not in practice, right? But you can imagine if you collect every single thing and measure it, in principle, you can reconstruct the book. Information is conserved in all of physics.
Quantum mechanics says information has to be preserved. But when a black hole radiates energy and eventually fades away, we end up losing something really important. Like, what was that thing actually made of in the first place? But perhaps there's more to uncover in this story.
So basically, if you can measure everything perfectly, you can predict what happened in the past and what's going to happen in the future. It's called determinism, that, right? So the old picture of black holes, and Stephen Hawking believed this for a long time, had a bet about it actually, is that they seem like they destroy information. You can just kind of see it. It goes to the end of time, right? It's gone. Even if you gathered all the Hawking radiation that had come off for trillions of years, there's no way you could reconstruct what went in. So therefore, if you jumped into a black hole, you'd be erased from the universe. But that breaks pretty much every law of physics, right? Things don't erase information. They scramble it up, make it difficult to read, but they don't destroy it.
To put it simply, this information could help us map out the entire universe, which enables us to predict basically anything.
So a black hole is one such rule breaker, since it doesn't follow the laws of physics as we know them. Once something crosses the event horizon, the information is gone forever, and there's no way to get it back.
So to work through this, scientists have actually come up with a bunch of different solutions to this puzzling paradox, each one offering its own possible answer, and we're going to explore some of them today.
One proposed solution to the information paradox suggests that a black hole holds on to its information until it shrinks to what's known as the Planck size. This scale represents the smallest measure in our universe, sort of like the finest point our cosmic microscope can see. So when a black hole gets this small, it's believed that the stored information gets released all at once.
This idea fits with both relativity and quantum mechanics, but it's not without its difficulties. Here's a point we all can agree on. The energy of a black hole at Planck size is incredibly tiny, yet the information packed inside is vast.
This leads to a quandary because it seems the information isn't coming out with the radiation, it stays put inside the black hole. For it to release this massive store of information, it would need to emit energy bit by bit, very slowly over time. In fact, it could happen for a much longer time, possibly even outlasting the expected lifespan of the universe.
The next solution is a bit bizarre, and we've hinted at it before. This is the extrapolation of the baby universe. That is, the universe we know and love does exist inside a black hole. We'll ask the question, what actually lies outside the observable universe, if indeed we live inside a massive black hole? We'll take the most extreme assumption, that our universe truly exists within the interior of a black hole, and that the cosmic horizon we see is nothing but the event horizon of that black hole, as viewed from the outside of it. Which is kind of rational since we can't see anything beyond it. At least not until the universe keeps expanding and the radius of that observable universe grows larger and larger over time. So what lies beyond this reality?
Here's the thing. The space outside our universe would belong to the parent cosmos, the larger reality in which our black hole was formed. But the geometry there wouldn't behave the way ours does, just like inside the event horizon of any black hole in our universe. 3 dramatic things happen in Einstein's equations. 1 is that the sign of the metric flips. 2, the space coordinate, or r, becomes time-like. And 3, the coordinate t becomes space-like. Inside the event horizon, every possible future leads towards smaller r. And that's why physicists say all world lines end at the singularity, because mathematically, r equals 0 acts like a future moment in time for everything that falls in.
And so the same thing applies when we extrapolate this idea to the other edge of our universe. Because the moment matter crossed the event horizon to create our universe, the roles of space and time switched.
Inside our universe, time flows away from the bounds, just as it flows forward from our Big Bang. But from the outside, space behaves as time does for us. So in that outer world, the dimension we experience as time passing might be nothing more than a distance you can walk, while what we call space might be what they experience as an unstoppable forward flow.
I guess that sounds a bit too complicated to describe that reality, but what if we try to visualize it in a way we can actually comprehend?
You know that here in our reality, we have 3 spatial dimensions and 1 temporal. The temporal flow always moves forward, whether we like it or not. Meanwhile, we can freely move within the 3 spatial dimensions forward and backward, left and right, or up and down by jumping. Now imagine flipping that scenario. This time, you could navigate along the time axis, literally moving to the past or the future. Yet, the spatial dimensions always move forward. So is there anything like that we can relate to in our daily lives?
It actually took me a while to find the right way to explain this, and actually I almost left this part out. But then I had a moment while walking through Chenxi Airport in Singapore. You've seen one of those moving walkways, right? You step on and they carry you forward. You could try to walk back, but no one does that. And even if you stand still, you're still moving forward. So that's the whole idea, that you're always being pushed in one direction, whether you like it or not. And then you might ask, what about the time options that we could navigate? Well, how about imagining each boarding gate as a freedom of choice for the time we could pick?
So if you decide to enter a specific gate, you'd be transported to a different point in time, where you could move around and explore it. So in that scenario, if we had an apparatus that could grant us access to different events, which allows us to teleport to any moment in time, the possibilities would essentially be endless. You could visit your own childhood bedroom. You could attend someone else's graduation and materialize nearby, or stand next to your friend during their childhood birthday.
In this case, time is very much navigable. The only thing you cannot do is go backward along the walkway. So if time is navigable in that sense, and if information is truly preserved through Hawking radiation, the way physicists suggest, then what if all that bits could survive not just a black hole, but the entire lifespan of a universe? Would remnants of it persist into what some refer to as the next cycle of the universe?
In 2019, Roger Penrose co-authored a research paper published in the Royal Astronomical Society titled Apparent Evidence of Hawking Points in the CMB Sky. In this study, he and his team reported several anomalies that could indicate a universe that preceded our own. They noted each anomalous spot would have originated from a highly energetic point-like source, resulting from the Hawking radiation of supermassive black holes in a cosmic eon prior to our own. Penrose suggests that some of these supermassive black holes from the previous universe might be connected to the conformally stretched Big Bang of the next eon. The observed anomalies are suggested as evidence of this link, implying that some information from a former universe could influence our current one.
So tying this back to the information paradox, this proposed solution hints at the existence of a long-lasting black hole remnant, which may prevent us from fully recovering all of the information. Now let's look at another angle based on what we discussed before. The entropy of a black hole is actually connected to the surface area of its event horizon. rather than its volume. Again, it's the so-called holographic principle.
According to this, the information of a black hole, while being three-dimensional, doesn't actually plunge into it along with Hawking radiation. It's imprinted onto the event horizon, effectively a two-dimensional boundary. It creates what's known as a stretched horizon. This allows the information to stay in a space where light exists, which avoids any conflict with causality and potentially resolves the paradox.
But we still need to keep in mind the no-cloning theorem. It states that the information cannot be duplicated.
At first glance, it seems like this rule is broken, but that's simply not the case. Here's why. Although it appears we have two sets of information, no single observer can ever see both simultaneously. One version is visible only to an observer falling into the black hole, and the other only to someone outside it. This concept is known as black hole complementarity. It suggests that these copies can't be seen or exchanged by multiple observers at the same time.
If we go back to the information paradox, there's actually one idea that we haven't talked about yet. What if the information isn't lost and it's not trapped inside either? What if it escapes into another universe? The idea is this. The insane density at the singularity could warp space-time so massive that it stretches out into a whole other universe through what's called an Einstein-Rosen bridge, or if we want to keep it simple, a wormhole.
In this scenario, the information tumbling into a black hole could travel through the wormhole and emerge in another universe. This new universe is much smaller compared to ours, and that's why we call it Baby Universe. Since this other universe is completely separate from our own, any information that crosses over is effectively lost to us but remains preserved there. The appealing aspect of this solution is that it doesn't conflict with any established principles, except for the challenge that we can't really prove this other universe exists. But let's consider this idea. Somewhere beyond the event horizon of a black hole, there might be a path to access this baby universe. So if it is possible, what would be the implications? Physicist Bryan suggests that in such a scenario, an extremely advanced civilization could capture all the Hawking radiation emitted, and they'll use it to reconstruct everything that the black hole has absorbed.
If you jumped into a black hole, then we do think that if a super being in the far future could collect every bit of Hawking radiation that came off the black hole for trillions and trillions of years and stick it into a giant quantum computer, then they could reconstruct everything that fell in. So actually, in some sense, you come out.
Most of what we know about black holes actually comes from studying them up close. And lucky for us, we've got just the right tools to do that.
This is the Very Large Telescope, or VLT, at the PERIL Observatory in Chile. This observatory houses 4 separate telescopes, each equipped with a primary mirror that is 8.2 meters in diameter. The VLT hosts sophisticated instruments, like the spectrograph for integral field observations. These devices help us observe black holes across different wavelengths, which offers high-resolution images of their dynamics, composition, and their behavior. Then we have the Event Horizon Telescope. It's a unique network of synchronized radio telescopes that are scattered across the globe. When they operate together, these telescopes create an Earth-sized virtual telescope. This configuration enables the Event Horizon Telescope to attain unmatched resolution levels. In 2019, this collaboration took the first direct picture of a black hole's event horizon. This monumental achievement verified the existence of black holes as previously theorized by Einstein. Another tool is the gravity instrument installed at the VLT. By combining light from the 4 VLT telescopes, gravity acts as an interferometer, which achieves incredibly high angular resolution. Its primary function is to investigate the close surroundings of black holes, things like the accretion disks, jets, and gravitational interactions with nearby stars. Assisting gravity is the Extremely Large Telescope, or ELT. Once completed in a few years' time, the ELT will be the largest optical and infrared telescope in the world. It'll boast a primary mirror with a diameter of 39 meters. This impressive size means it will have extraordinary light-gathering capabilities. With advanced adaptive optic systems, the ELT will compensate for atmospheric distortions. This state-of-the-art telescope will play a key role in studying black holes and other celestial phenomena. It will allow us to investigate the growth of supermassive black holes and the relationship between them and their host galaxies in more detail than ever before.
So as our instruments and the data gets better, we can start asking questions. If spacetime can actually bounce or even repeat, then what does that evidence actually say?
Modern astronomy is no longer confined to theory. With instruments like the James Webb Space Telescope, we can now look deeper into time than ever before. And what we're finding is both surprising and unsettling. In September 14, 2015, LIGO detected a signal carrying information about a pair of distant black holes that had spiraled together and merged. It looked something like this. That signal had traveled for about 1.3 billion years across the universe before reaching Earth. It did not emit light, but instead carried gravitational waves, tiny ripples that stretch and compress space as they move. This marked the first time humanity had ever heard the universe through the warping of space-time itself. And a decade later, in January 2025, another merger event, named GW251-114, gave scientists an even deeper insight. By analyzing its gravitational wave frequencies, researchers verified Hawking's second law of black hole mechanics. As we've mentioned before, it's the fact that the total surface area of black holes can never decrease. This confirmation came from studies at Northwestern University. In the same year, James Webb also revealed something even more puzzling. You see, in a random universe, we would expect roughly equal numbers of galaxies rotating clockwise and counterclockwise. But the deep field observations suggested otherwise, that most galaxies appear to rotate in the same direction.
This one really gets you thinking. If the universe was born from a truly random explosion like the Big Bang, then galactic rotation should also be random, right? So could it be that our universe has been rotating since the beginning? And if so, where did that spin originate? This ties back to our earlier discussion today.
Professor Poplawski offers one possible explanation. He says that our universe was born rotating. It's a natural consequence of being formed from within a spinning black hole in another universe. And so, to an external observer, that black hole would appear as a dark point in their sky. But to us, inside it, that point would be the entirety of our cosmos.
In the end, this explanation aligns with the black hole cosmology hypothesis, which suggests that our entire universe exists inside a black hole.
The horizon of the universe has all the same properties as the event horizon of a black hole. We would be living evidence of a universe inside a black hole.
And so once the universe came into existence, how did it evolve into what we see today?
In 1985, Stephen Hawking and James Hartle described in their work on the origin of structure in the universe
that before there was space, time, or even atoms, the universe was governed by quantum fluctuations. They're tiny, random jitters, and like the waves of energy flickering in and out of existence.
And then, as the universe rapidly expanded during the event known as cosmic inflation, those minute fluctuations were stretched across enormous scales, which would then become the seeds of everything: galaxies, stars, and the vast cosmic web we observe today.
Inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. There was doubling in size.
The authors went even further, suggesting that the universe itself can be seen as one giant quantum wave.
Before our specific universe came into being, there existed only the possibilities of many universes, and ours was one that became real. This transition from possibility to reality is explained through what physicists call the freeze-out moment. During inflation, space expanded so rapidly that those quantum waves could no longer change. They became frozen into place. Random fluctuations solidified into real structures and settled the blueprint for all matter and energy that followed. And so from these frozen ripples, the universe began to take form. What started as chaotic quantum energy eventually became the universe we know today.
All fields, all quantum fields, have tiny fluctuations in them. They are not isotropic either.
Quantum physics enabled this universe.
Despite our scientific advancements to study a black hole, there's still a great deal we don't know about it, especially the inner workings of this giant beast. Theoretical predictions have provided us with an understanding of their basic structure, but the extreme conditions that exist within a black hole remain largely unexplored. Back in 1985, Carl Sagan was working on a science fiction novel called Contact, which eventually became a well-known film. The plot takes an interesting turn when the main character falls into a small black hole on Earth and emerges from another black hole light years away in space.
When you put like quantum physics and general relativity and you try to come up with some bigger understanding, deeper understanding, string theorists have been all into this, you get a multiverse. We didn't pull that out of our ass, that came out of the equations.
A lot of hypotheses out there suggest that black holes could actually work as natural time machines. And honestly, there's actually some real science behind it.
One key concept is time dilation, which happens because of the incredible gravitational pull that black holes exert. Time dilation comes from Einstein's theory of relativity. It tells us that time doesn't pass at the same rate everywhere, but it can slow down with the increase of gravitational force. This difference in the flow of time between various parts of space-time is enormous near large objects. And so, black holes have become a stage where time dilation is pushed to its limits.
We can definitely travel into the future by moving faster relative to everybody else. And then you'll come back less aged than those you left here on.
Consider the following thought experiment. Imagine a spaceship orbiting a black hole. The crew are so careful not to get pulled in. These guys would experience time moving slower than for those on Earth. When they return, they'd find an Earth that has aged significantly into the future, perhaps hundreds or even thousands of years. Some scientists even suggest that the severe warping of space-time within and around black holes could fold space and time onto itself. This could lead to a closed time-like curve, also known as CTC, or a time loop. A CTC could allow for time travel into the future, and possibly even into the past. This time loop concept proposes that paths exist through space-time that loop back to the starting point in time.
But whether such curves exist in our universe is still up for debate.
It could have some profound consequences for our understanding of time, causality, and the very fabric of reality.
Of course, we're only scratching the surface here. There's a lot more I could explain about the mechanics behind this concept. Just drop this emoji in the comments if you'd like us to feature this idea in another video.
But the staggering message is this: what lies outside our observable universe might be a realm beyond our comprehension. Because through evolution, we've been conditioned to think and perceive within the familiar boundaries of the reality we inhabit. So even the simple idea of space and time swapping feels too complex to comprehend. That explaining it requires layers of analogies.
And maybe, if all those analogies were stripped away and we were faced with the raw, logical structure of what truly exists beyond our universe, we simply wouldn't be able to comprehend it, let alone experience it. Schwarzschild. This incredibly dense object forms when a massive body collapses to a specific size, something known as the Schwarzschild radius.